Previous class we discussed about the Cascade H bridge. So in continuation to that, in case of Cascade H bridge, so these H bridges, so either we can connect it in star or we connect it in delta, right? So if we connect in star, so this star connection, so this is what, so this is the star connected H bridges. Similarly, we can connect this in delta. So likewise, so here there is no neutral point here. So here, so if you notice that this is the point here, so this is coming from C phase. Similarly, so this is coming from here and this is coming here. So this is forming a delta connection. So it is forming a delta connection. So this modular, this Cascade H bridge, right? So this comes under the family of MMC. So that is known as modular multi-level converters. Modular multi-level converters. So actually there are 4 types of modular multi-level converters, so that we will going to discuss in later point of our course. So in this, the first one is single star. The first one is single star bridge cells. Second one is single delta bridge cells. And third one, double star bridge cells. And fourth, we have double star chopper cells. So these are comes under the family of this Cascade H bridge, right? So this comes under the family of modular multi-layer converters or modular multi-layer inverters, right? So right now there are 4 topologies under this modular multi-level converters. So these modular multi-level converters are used for extremely high power applications. So where the power is in the range of 100 kilowatt, 100 kVA and 100 MVA range. So here, so the first one is single star bridge cells, single delta bridge cells, double star bridge cells, and double star chopper cells. So we'll go into discuss about this at later point of our course. So the single star bridge cells, the CHB, so this is also known as single star bridge cells. This Cascade H, the CHB, so this is known as single star bridge cells. So why it is known as single star here? So we have star connection here. So bridge cells are connected in star connection. So that's why it is single star bridge cells. So it is known as SSBC, single star bridge cell. So CHB is also known as single star bridge cell. Similarly, if you notice that, so this is connected in delta. Again, this is a star connection. So that's why it is known as single delta bridge cells. So bridge cells are connected in or forming a single delta. So that's why it is known as single delta bridge cells. Right. So now the question is, so we have something like this. So let us assume that if you want to design a 3.3 kV CHB inverter, Cascade H bridge inverter, it may be a single star or single delta. Right. So now how to choose So how to choose this DC voltage? How to choose this DC voltage, or how to choose this cascade number? Right. So first thing is, so you are aware that, so here the thing is that if you choose or if you fix this cascade number, so you need to choose the DC voltage. For how much DC voltage you're supposed to get, so this much of voltage. So this nothing is given means, so this is a line voltage. If this is the line voltage, so what will be the phase voltage? If this is line voltage RMS, so what will be the phase voltage? So what is the phase voltage? How much is the phase voltage in case of star connection? What is the phase voltage if the line voltage is 3.3 kV?
1.905.
1.905. 1.905. So it roughly it is 1.9 kV. It's roughly 1.9 kV, right? If you want to design a 3.3 kV inverter, so that is line voltage RMS value, the phase voltage must be 1.9 kV. So that means the voltage measuring from here, this is A phase, to this one. So its line voltage, sorry, its phase voltage, and its RMS value is 1.9 kV. Right. So let us assume that you have two H bridges per phase. If we assume that we have two H bridges per phase, okay, each one is VDC. So what is the maximum voltage that can achieve? So that is 2 VDC, right? If each one is VDC, so that can get a maximum voltage of 2 VDC. So it will be something like this. You have 0 level here, VDC level, and this is 2 VDC, 0 VDC and 2 VDC. And after that you have, so it is the shape of phase voltage. So what is the peak value of this phase voltage? What is the peak value of this phase voltage? So this is 2 VDC, right? Peak value is 2 VDC. Okay, but we have this 1.9 kV, so which is its RMS value. So what is the peak value of this one? So this 1.9 kV into root 2. So that is its peak value. So how much this is? 1.9 kV into root 2?
2.68.
2.68. Okay. So that is the peak value. If you assume that, so this waveform is a close approximation to a sine wave. This waveform is a close approximation. So in this case, so it is supposed to be equal to 2.68 kV. It is supposed to be equal to 2.68 kV. So from this, so what is the approximate value of VDC? What is the approximate value of VDC? Two VDC is 2.68, right? So what is VDC? 1.34 kV. The meaning is, right? So meaning is, if you choose this VDC as 1340 volts and this is at 1340 volts, if you have two H bridges per phase, right? So in that case, so approximately you will get a voltage which is equal to 2.6 V and the line voltage which is approximately equal to 3.3 kV. So why it is approximately? Because so this is the actual output, right? And this is the our right? So this is the close approximation of this sine wave. This is the close approximation of this sine wave. So now the question is, so if we increase the cascade number, right? If we increase the cascade number, so likewise, for example, so you are increasing this cascade number. So this waveform is more close to a sine wave, right? So this waveform is more close to a sine wave. So that means if this is 3.3 kV, so line voltage is supposed to be phase voltage is supposed to be 1.3, 1.9 kV, right? So its peak value is 1.9 kV. So that means this peak value is 1.9 kV. That is root 2. So this is equal to how many you have? 4 into VDC. So this 4 into VDC, that is equal to its peak value. So from this, so what is VDC? What is VDC?
0.67 kV.
0.67 K. So that means roughly it's 6.670 volts. So this was must be 670 volts. So this is 670 volts. This is 670 volts, and this is also 670 volts. So that this sinusoidal waveform, so which is close approximated to the phase voltage, so which is having a RMS value which is equal to 1.9 kV. So from this line voltage RMS value is 3.3 kV. The thing is that, so this approximation, so these are approximate values, right? So you can get the something near to that, okay? Something that closer to that waveform, so you can get. So if you want the exact value, so you need to slightly fine tune this one. You need to slightly fine tune this one. So what we had to do is, you need to do the simulation for taking 670 as 670 volts and operate at modulation index MA equal to 1 or something like that. So from that, measure the phase voltage and line voltage and check whether it is equal to 3.3 kV and 1.9 kV. Right. If not, we need to slightly adjust this value. We need to slightly adjust this value. Okay. So here, so this will work out if the cascade number, if the number of H bridges are more, if the number of H bridges are more, if n is a large value, so in that case, right, the accuracy will be high. Right. So in that case, the accuracy will be very high. If n value equal to, for example, n equal to 2 or n equal to 3, so in that case, the stepped waveform, so which is not a closed approximation to a sine wave, right? If this is the case, so this is n equal to 2, for example. So this is not a it's a not close approximation to a sine wave when compared to, so that n value is larger, right? So here, in this case, the error will be slightly higher when compared to the other case, so where the n value will be large. So under these cases, right, so for low value of n, if you select n value low, maybe for n equal to 2, 3, 4, somewhere n equal to 2, 3, 4, 5. So how you will choose that one? So for each 1000 volts, right, of DC voltage, for 1000 volts of DC, right, so you will get a 625 volts AC across each bridge. For 1000 volts, if this is 1000 volts, right, so this is 1000 volts, so roughly you will get 625 volts AC across each bridge. Okay. Right. So this is usually followed for lower value of, what we say, for lower value of cascade numbers. Right. So this is how we will select the cascade number, or how many how we will select the DC voltage. So next thing is, so how to select this cascade number, right? So how to select this cascade number? So that all depends on the number of or the devices, so that device blocking voltage, right? So in this particular case, right, so we are selected, so this VDCS 1340 volts. So this VDCS 1340 volts. So that means this device is supposed to block 1340, this device is supposed to block 1340, right? So let's assume that you have only 1200 volts devices are available. So in this case, what we have to do is you need to add another H bridge, right? Either n equal to 3 or n equal to 4, you need to select. So this DC voltage will be reduced. So that the DC voltage will be reduced. In that case, you can use the lower voltage devices. And also the waveform quality is also increased. In other words, the THD of the waveform is also improved because the number of levels are high, so therefore the THD will be reduced. So depending on the rating of the devices available, so we'll choose the cascade number. So depending on the line voltage and the phase voltage RMS value, so we'll choose the DC voltage. Right. So this is for star connection, right? So in case of delta connection, so what will be the change? So in case of delta connection, so what is it an advantage or disadvantage in case of delta connection? So in case of delta connection, the phase voltage and line voltage both are same, right? If it is 3.3 kV phase voltage or line voltage, so that means the phase voltage is also 3.3 kV. Okay. So now the phase voltage peak is 3.3 kV, see into root 2, right? So that is the peak value. So this will be equally divided to, for example, you have 2 H bridges per phase, right? So that means it will be equally divided to 2. Right. So how much it is supposed to increase? So that means here, earlier you got 1.34. So now you got 1.34 into root 3. Agree? So in case of delta connection, right, the voltage across each H bridge, is supposed to be increased by root 3 times. Why? Because the phase voltage and line voltage both are same. The phase and line voltages both are same. So in other words, if you keep the cascade number same, so this delta connection required root 3 times root 3 more number of H bridges per phase when compared to the star connection. Right. So if you have the same rating here, so in case of this delta connection, you require root 3 more number of H bridges per phase. We assume that the cascade number of these two converters are same. So that is the disadvantage with this delta connection. But this delta connection is used in applications so where we are compensated. For example, you are aware of the Statcom, right? Static synchronous compensator. You might have studied in the facts course. So why this Statcom is used? So why this Statcom is used? Why Statcom is used in transmission lines?
Statcom supply
So
harmonic
voltage control.
components.
Reactive power compensation.
Reactive power compensation and voltage support, right? For example, if you want to maintain a voltage at particular bus at 1 per unit or something at desired value, so that is for voltage support and reactive power compensation, and also to increase the power transfer capability of the transmission line. So we use the Statcom, right? So especially so by compensating the reactive power, right, all these things can be performed. Okay. So here the Statcom is used in transmission lines, So this is compensating the reactive power. So in case of this transformer, for example, if the load is a arc furnace load, so this load is arc furnace load. If you might study the power quality course, in arc furnace course, arc furnace loads, so that will inject the negative sequence harmonics or the negative sequence reactive power. You might have studied that arc furnace at some point of time, two of the phases will be in brief short circuit for a brief period of time. So that may cause the reactive power. So that reactive power is in negative sequence. Normally we have phase sequence, right? ABC sequence, but the reactive sequence, that means the reactive power is rotating in the opposite direction as of the conventional one. So that means it is producing a negative sequence reactive power. To compensate that negative sequence reactive power, so what we have to do is we will use this Statcom, so which is composed or which is based on this Cascade H bridge. If this based on this Cascade H bridge, right? So that is used to compensate the negative sequence reactive power. So why exactly we used this one? Because we have this delta connection. Okay. So what is the good thing with this delta connection is this? So whatever that negative sequence reactive power is there, so that is circulated in the delta. You are aware of this, right? Zero sequence harmonics are circulated in the delta connection. Similarly, this negative sequence reactive power, so that is also circulated in the delta connection. So this current is the reactive power, the current that causes the negative sequence reactive power, so that is circulating in this delta connection. So therefore, the source is or the supply is free from this negative sequence reactive power. Okay. So here the circulating current, so you have only one circulating current, right? So that means, so if you have circulating current, you have 1 degree of freedom. You're aware of the circulating current, 1 degree of freedom. So you have only one path for the circulating current. So usually the number of paths for circulating currents, that is denoted with circulating currents. So in this case, it is 1 degree of freedom. So circulating currents are in 1 degree of freedom. So where we have this double star chopper cells and double star 360 cells, so that have circulating currents either 2 degree of freedom or 3 degree of freedom. So that we will discuss. So if you have one delta connection, something like this, if a delta connection, for example, if the load is connected like this, so the circulating current will be rotating in this right. It will not come out of these phases. So that means you have only one path for the circulating currents. It is known as 1 degree of freedom. Circulating current as of 1 degree of freedom. So this is about the selection of cascade number and choosing the DC voltage based on the voltage requirement. So generally the cascade number, so that all depends on the number of available switches, and right, if we choose the larger value of cascade number, the size will increase. So somehow, so we need to optimize this. So next thing is, so how to power these H bridges. As we already discussed that, so these H bridges are isolated one. So that means there is no physical connection between these H bridges in these H bridges in any of the phases. Either in phases there is no connection, or with other phase, so there is no physical connection. So this is one of the H bridge. Okay. So this is one H bridge. If you notice that the H bridge is powered from a 3-phase diode bridge rectifier. The H bridge is powered from a 3-phase diode bridge rectifier. Right. So again, this diode bridge rectifier is connected to some other supply. Right. So here, same thing. So here also we have the H bridge is there, but this is supplied from a rectifier circuit. This is active rectifier, right? We have studied this active rectifier. So what is the difference between these two? What is the difference?
Firing angle control.
Why firing angle control? This is a diode only. What is the main difference between these two? First thing, right? So this is the uncontrollable devices. So these are uncontrollable device, and the power flow is from only one direction, right? Okay. So it will not, power flow will not be in the other direction, right? Okay. So that means, so this is suitable for uncontrolled applications. So where we don't require regeneration, because these diodes are not capable to regenerate, right? So these are not regenerative, and this is used for uncontrolled applications. So here this output voltage is fixed one because of these diode bridges. Okay. So let us assume that these are replaced with thyristors. If you replace with thyristors, in that case we can control the output voltage. We can control output voltage here, or we can control the DC link voltage, right? And the other thing is, what is the other thing? So we have regeneration is also possible, right? If the load is, for example, we have connected some load is, right? If the load is active load, you might have know the loads, right? So load may be active or passive. So meaning of active load means the load is capable of regeneration, right? The load is capable of regeneration. For example, you have more something like the DC machine or something like an induction motor is there. Somehow this motor is rotating, or somehow the motor is capable to rotate in the opposite direction. So in that case, some significant amount of the energy or significant amount of the power that is transferred from the load to source, right? So to get that source or to get that power, right, so we must have a mechanism, or we must have a converter, so that can allow the power flow in both directions. Okay. So these thyristors will allow power from both directions. So therefore, it can be have, so regeneration capability. Regeneration is possible. Only thing is that, so if your thyristors are there, so thyristors are slow devices. Okay. So once you turn on, because these are the line commutated thyristors, so we need to wait until the zero crossing of the voltage or zero crossing of the current achieves, right? So therefore, so here this regeneration is limited. So here this regeneration is limited, and moreover the control of the voltage is also not very fast because of the firing angle control, which is slow. So that is the disadvantage if you have a thyristor controlled rectifiers, and moreover this is also causing reactive power. So this is a active rectifier. Active rectifier. Thing is that, so it is possible to regeneration is possible. Regeneration is possible. The control is also possible. You can precisely control the output voltage. And another thing is, if the source, right, on the source point of view, so we can make the reactive power. We can make the reactive power to 0 or the reserve value, and also you can operate at unity power factor. And also you can operate the source at unity power factor because of this rectifier. You might have studied this in APC course, and also you studied this in lab course, right? So this is known as active rectifier, three-phase active rectifier. So from this three-phase active rectifier, so this DC link is regulated. So from this, it is given to the H bridge. Okay. And also some other applications, right? So here, these applications where the active power transfer is taking place, okay, where the active power transfer is taking place. So here this active power flow is possible, right? Okay, in case of applications, so here this is another applications. So here a fixed battery here. So this is maybe a battery, or it may be a PV panel, or it may be a something like maybe a energy storage device. It may be energy storage, anything. So here also real power transfer is taking place from this to here. The real power transfer is taking place. the thing is that, so these are self-sufficient, right? So whereas here, so this is coming from external supply. So here the real power transfer is happening from the external supply. So whereas here from the self-sufficient, it may be PV panel or it may be from energy storage element or something like this. Right? So but whereas we have applications, so where there is real power requirement is not, real power transfer is not required, but you require a reactive power. For application like Statcom, right? So basically Statcom use it to compensate reactive power, right? So ideally or theoretically, it's supposed to compensate or supposed to, right, supposed to transfer the reactive power. So in these applications, so what we have to do is, so instead of these DC sources, right, so these sources are replaced with a capacitor. You might have studied in Statcom, right? So that means the DC source is replaced with a capacitor. So we have some charging mechanism, right? We have some mechanism to charge this capacitor, right? So here we need to regulate the voltage across capacitor. We need to regulate voltage across capacitor so that it will work properly. So that means we have three options. The first one is where we require real power transfer. For example, for applications like motor drives, so where you require real power transfer every time. So in that case, you require a supply, three-phase or single-phase power supply. So with this front-end converters. So with this front-end these are front-end converters. Second applications, you require either a battery or a fixed a PV panel, or you require some energy storage device, or you require an ultra capacitor likewise. Okay. So this is usually the application for this. It may be a EV application, electric vehicle application, or sometimes you require this for a grid connected applications. If the PV panel is there, if you want to connect this grid, so if you have all this setup, so that setup instead of this one, so you have grid here. Right. So other applications, so where the real power transfer is not required, so in that case, so here, so we have to use the capacitors. Somehow we will maintain the voltage across this capacitor. So how exactly we will maintain the capacitor voltage, so that we will discuss in later classes. Just remember this much for time being. So here we replace with capacitors. So we have an additional controller to regulate the voltage across the capacitors. Where in this predominantly we have reactive power transfer. So only a small amount of real power transfer is taking place to overcome the losses that occur due to the capacitors. That we will discuss. Right. So this is about the Cascade H bridge. Right. So now in case of real power transfer with some supply, so where exactly you require isolated DC supplies. So this is the schematic diagram. Okay. So here K cells are there. So this is 1, 2, 3 up to K cells are there. So this is for a motor. Okay. So this is the front end. So this is each cell. So each cell is having one H bridge. So this is another H bridge and another H bridge. You can see here. And each cell, it requires an isolated supply. Each cell requires an isolated supply. So this is how this isolated supply is providing. So you have a 3-phase rectifier is there, another 3-phase rectifier is there, another 3-phase rectifier is there. So this is supplying from a transformer. So where you have multiple windings. So this is primary. So we have several right. We have k number of secondaries are available. So this is the first secondary winding. So this is second secondary winding, and this is the kth secondary winding. Right. So what exactly this arrangement is known as? What is this known as? What is this converter is known as? What is this converter is known as? So this is known as multipulse converter. So this is known as multipulse converter. So here, so there will be phase shifting between the converter so that the harmonic cancellation can be done. So that we will discuss in the, maybe in next class we'll discuss these things. So here, to power up the each H bridge, you require a multipulse converter. So this is for A phase. Right. Similarly, you have for B phase, and similarly you have C phase. Right. So either all the phases are connected to, right, all the phases are connected to a single multipulse converter, or we have a different multipulse converter for different phases. Right. So this is required only when you require a real power transfer. So this is especially for motor applications. So why this is required? If this is only provides the isolation. So this only provides the isolation. If this is not there, so these diodes are direct, this is directly connected. So that means there is no isolation among the H bridges. So once this is operating, the operation of this one is affected, the other H bridge. So this is about this cascade H bridge converter. So in next classes, so we'll discuss more about these multipulse converters and other concepts. So next we'll move to the next one, so which is flying capacitor, multi-level inverter. Flying capacitor, multi-level inverter. So this is structure of a 5-level flying capacitor, multi-level inverter. So this is looks like a cascade, look like a diode clamp. The thing is that, so here also for 5-level, so 4 upper devices are required and 4 bottom devices. You have A phase here. Similarly, B phase, C phase. So here the intermediate levels can be obtained by using a pre-charged capacitors. So this is a pre-charged capacitor which is charged to E voltage. So there is another one, right? See, which is connected to 2E voltage. This is connected to 3E voltage. So these are the pre-charged capacitors. So this is the DC link. This entire thing is DC link, which is common to all 3 phases. This DC link is common to all 3 phases. Similarly, this is charged to E. So this is charged to 2E. These 3 are charged to 3E. So each one is E. So here, so this is complementary to this bottom one. So this is complementary to here, and this is complementary to this one, and this is complementary to this. So whereas in diode clamp, so this first one and first one, so both are complementary, right? So this is slightly different. This upper one, this S1 is complementary to this bottom one, and this is complementary to this one. So come to its operation, right? So come to its operation. So when this S1, S2, S3, S4 are on, right? What is the voltage across these 2 points?
4E.
4E, right? Okay. So if one of the switches is off, what is the voltage across S2, S3 and S4?
3E.
What is the voltage across S3, S2, S3, S3? What is the voltage? So how it is connected? These 3 switches are on. This is off means, so this switch is on, right? So now these 3 switches are on. Okay. So this is connected here, and this point is connected here, right? So what is the voltage? How much voltage you are getting?
3.
3E, right?
3.
You are getting 3E voltage. Similarly, if these two switches are on, so this is off, so this is on and this is on. Okay. So that means this is on and this is on, right? So what is the voltage across A and N?
2.
So these two are connected, right? These two are connected. So that means it will be something like this. So now only, so this switch is on. Okay. These three switches are on. What is the voltage?
E.
E.
So it is connected only to this capacitor. Right. So now the question is there any alternative way to obtain E voltage? Is there any alternative way to obtain E voltage instead of this? So you have any alternative way to obtain E voltage? Any alternate way to obtain E voltage? Is there any alternate way to obtain E voltage? So this is 3E, right? So this is 2E. So can we subtract these two? Is it possible to subtract those two? Is it possible to subtract those two? Or if this switch is on, right? If this switch is on, so these three switches are off. Okay. So that means, so this is off, so these are on. So what is the voltage across A and N?
-3.
-3. -3.
Minus
TE.
how much voltage?
Is
How much voltage? So these are on, right? Okay. So this is connected here. Agree? So this A is connected to this negative plate, right? So now this is on. So this is connected here. So what is the voltage between these 2 points? This voltage is, what is the voltage here? This is 4E, right? And what is the other voltage? So this is 4E, agree? And this is how much? 3E, right? 4E minus 3E. So what is the voltage?
E.
E.
So that is giving E voltage, right? Understood? So this is 4E voltage here, right? But here, so this point voltage is 3E. So 4E minus 3E, because this is connected in the opposite direction. Similarly, This is switch is on, S2 is on, right? This is off. So now tell me what is the voltage across? So only one upper switch, S2 is on. So what is the voltage across? A and N. Only one upper switch is on. What is the voltage across A and N?
E.
So which is equal to E, right? So how it is E? So this point is connected here, right? Okay. And the other point, so this is coming like this, and this is connected to E. Agree? So this is connected here. Understood? So this entire voltage is E. So this at this point, this voltage is 3E. Okay. So at this point, this is the like this, right? At this point, this voltage is 2E. So what is the voltage here? What is the voltage? 3E minus E. So 3E minus 2E. So voltage is E. So you can get E voltage. Understood? So this voltage is 2E and this entire voltage is 3E. Similarly, the thing is that, right, so what we can understood that if you want E voltage, right, if you want E voltage, so this is 4E and this is 3E. If you subtract these two, so you can get E voltage. So that is one option. Or, so this is 3E and this is 2E. If you subtract these two, you can get E voltage. Similarly, so this is 2E and this is E. So you can subtract these two, you can get E voltage. Or operating this alone, so that can gives you E voltage. Right, operating this alone, that gives you E voltage. So that means if S1 is on, right, only in the upper switch, so these two can be subtracted. These two are subtracting. So if this S2 is on, so these two are subtracting. This S3 is on, so these two are subtracting. Similarly, this S4 is on, so only you have access to one DC source. So that is for E, you have four possibilities are there, right? You have for 0 voltage, so all the upper switches are off, so all are off, right? So that means only this bottoms is connected, so that means you can get 0 voltage. That's straightforward, right? So for 2E voltage, so there we can also achieve 2E voltage. So how to get 2E voltage? So how to get 2E voltage? So we have
By
one
keeping
possibility
S1
is,
strong.
right, one, there are several possibilities are there. So you can turn on these two switches, right? So that gives you that I can access these 2U voltage, or, right, or we can subtract these two. So that means if you want a subtraction between this one and this one, so that also gives you 2U voltage. So now tell me which switches you need to turn on. So which switches you need to turn on?
S1 and S2.
S1, S2.
Yeah, right. So if you turn on S1 and S2, right? So this is connected here. So that means this point is connected here. So these S1, S2 are on. So these two are off, right? So that means these two are on. So this is off, this is off. So this is connected to A. So that now you are getting 4E minus 2E. 4E minus 2E. Okay. Similarly, so we have 3E is there. So this is 3E and this is E, right? So now if you want 3E minus E, so which switches you need to turn on?
S2 and S3.
S2 and
S3.
yeah, S2 and S3. No. S2 and S4, I think. So obviously this is if you want this one, so this must turn on, right? That's why you have access to this one. Okay, so it must be S2 and S4. So this can be summarized something like this. Okay, right. This can be summarized something like this. If S1, S2, S3, 4, all four are on, so you can get 4U voltage. All four are on, you can get 4U voltage. If any three are on, any three, okay. If any three are on, you can get 3U voltage. If any two are on, among these four, so you can get 2U voltage. If any one is on, you can get E voltage. If all are off, you can get 0 voltage. That's simple. So we have switching redundancy here. If all switches are on, you can get the full voltage. If one switch is off, right, you can get 3E voltage. If two switches are off, you can get 2E voltage. And if three switches are off, you can get E voltage. And all switches are off, you can get 0 voltage. That's all. So this is how a multi-level voltages, so across this one is you can obtain, right? So similarly from B to N, so from B phase to N, you can get voltages starting from 4E to 0. Similarly for C phase, you can get 4E to 0. So from that you can obtain the line voltages between A to B. So it will vary from 8E to minus 8E. It will vary from plus 4E to minus 4E. So that means you can get 9 levels in the line voltage maximum. Right. So this is flying capacitor multi-level inverters. The only thing is that we need to maintain the voltage across this DC sources. Right. So we need to maintain the voltage across this DC sources. So that is the only drawback. So that is the only drawback here. So we need to maintain the voltage across the DC sources. So that means this must be pre-charged to E. So this must be pre-charged to E. So this entire thing, if you have individual capacitor, each must be pre-charged to EE. If it is a single capacitor, that must be pre-charged to 2E. Similarly, this must be pre-charged to 3E. And this is DC link, right? So this DC link, how this DC link can be obtained? By using a multipulse converter. It may be batteries, or it may be batteries, or it may be multipulse converter outputs, or it may be capacitors. So this is DC link. So how this DC link is designed, so that we'll discuss in the next class. So you have any questions in today's class? You have any questions?